right, 3.2, periodic trends. Okay, we'll be doing this in two parts. Part one's today. Periodicity, the tendency to recur at intervals. Okay, so what we're looking at is how things change in a systematic way as we move across a period or up or down a family. Now, these are trends. Trends means a general tendency. These are not laws. You will see exceptions for the various properties that we'll be looking at, but we're interested in just the overall trend. First, atomic radius, which is the distance from the nucleus to the outermost electron, as you might guess. So looking at a real simplistic model of the atom, excuse me, it would be the distance from the nucleus to the outermost electron, wherever that might be. And the trend decreases as you move across a period due to an increase in nuclear charge because we have more protons. So as we move across a period, you're going to be adding more and more protons to the atoms because the atomic number gets greater and greater and greater. So the positive charge of the nucleus becomes greater. It'll pull the electrons in more and more tightly. So as we go across a period, atoms get smaller and smaller and smaller. Now, if you go down a family, it increases. As you go down a family, higher energy levels are occupied. So for example, this is lithium. Its outermost electrons are in the 2s. Sodium is in the 3s. Potassium is the 4s. Rubidium is the 5s. So we're adding the outermost electrons are in higher and higher energy levels. And that trend is the same as we move down any of the families. The atoms get bigger and bigger and bigger. Radius increases. Ionic radius. Now this is not a trend as we move across the periodic table, just looking at the size of an atom, it becomes a positive or a negative ion. The radius decreases as electrons are lost. So cations are smaller than their neutral atom. So sodium, when it becomes a positive ion by losing an electron, it becomes smaller, which is just common sense. Just imagine if you were to remove all of its electrons, eventually you would have nothing left but the nucleus. So every time you remove an atom, the atom gets smaller and smaller. An electron. The atoms get smaller and smaller and smaller. Conversely, the radius increases as electrons are added. Anions are larger than their neutral atom. So chlorine almost always has a -1 charge. When it gains that electron, it becomes bigger. So both of these are common sense. Take away something, it gets smaller. Add something, it gets bigger. Okay, let's do a little practice. Circle the ion with the largest ionic radius. Well, all three of these are anions, but it is the third one that has 3 electrons, whereas the other 2 have fewer. So it must be the larger of the 3. It has more electrons. It's the same element. Circle the ion with the smallest ionic radius. Okay, now these are a little bit more challenging because we're looking at different elements. However, if we think about their atomic number, so we know that sodium has 11 protons, it's holding on to all the electrons. Magnesium has 12, fluorine has 9. And so what they all have in common is that they have 10 electrons. Sodium, the +1 charge, has 10 electrons. Magnesium with the +2, 10. Fluorine with the -1, 10. So all we need to do, or to ask ourselves to answer the question, is which one has the greatest positive charge? Because the one that has the greatest positive charge will hold on to the 10 electrons more tightly. And so for that, all we have to do is look at the atomic number. Magnesium has 12 protons holding on to the same number of electrons that sodium and fluorine have, but it has more protons, so it's holding on to them tighter. Higher nuclear charge. Ionization energy. The first ionization energy, the energy required to remove the outermost electron from a gaseous atom. Now, what we mean by a gaseous atom is just an atom all by itself. It's not bonded to anything else. So let's look at an imaginary element, X. So this would be losing an electron. So when it loses an electron, here's the electron that's being lost, it has a positive charge. It takes a certain amount of energy to pull an electron away. The trend, it's inversely proportional to the atomic radii. That is, the smaller the atom, the greater the ionization energy. Okay. So just think of it like this. To remove this electron from the nucleus would be take a little bit more energy because it's more tightly held. It's closer to the nucleus. Whereas to remove this electron, it's further away from the nucleus, and so it'd be easier to remove. So when we try to compare ionization energies between atoms, we really just need to go back to the atomic radius. Whichever is the smaller atom would have the higher ionization energy, because it would take more energy to remove that electron. The larger the atoms, the easier it'll be to remove an electron. All right, let's do some practice. Circle the element with the largest ionization energy. So for this, we want to look at the periodic table. Now, you're not going to be just given 3 random elements. So these are fairly close to each other, and they're right next to each other, actually. Okay, so selenium, bromine, and chlorine. So what we want to do here is ask ourselves which has the smallest radius. Remember, the smaller the atom, the larger the ionization energy, the more energy it'll take to remove an electron because the electron's closer to the nucleus. So all we need to do is just look at 2 at a time. Well, let's look at selenium and bromine. Well, we know that atoms get smaller as you go across a period, so bromine is going to be smaller than selenium. So of the 2, it wins. But we also know that as we go down a family, the atoms get bigger. So that means that chlorine is going to be smaller than bromine, which is smaller than selenium. So it would have to be chlorine. Do one more. Circle the element with the smallest ionization energy. Okay, so for this, we want the largest radius. And sodium, potassium, and rubidium are all in the same family. We know that the atoms, well, here's my hint, the hint. Which element is largest? Well, we know as we go down a family, they get bigger and bigger. So it would have to be rubidium. It's the largest of the 3, so it would take the least energy to remove an electron. Okay, now these are the trends for periods 1, 2, 3, and a couple from 4. And as you can see, the trend, so this is the ionization energy and the atomic number of protons. And you can see the trend is just as we've said. So this is the first period, ionization energy increases. The second period increases. The third period, the fourth period increases. Now, there are a few blips in this. Now, you will be learning about those in IB Chem 2. So I'll leave it to Ms. Wall to teach you that, or you could look it up yourself. If you're interested, you could search why is there a difference in the ionization energy between nitrogen and oxygen? Hint, it has to do with the number of paired electrons. But again, all you're responsible for is the trends. Let me be clear, you don't need to know this chart. You just need to understand what it's trying to tell you. Successive ionization energies. There's an increase in the ionization energy after each electron is removed from an atom. So here we're talking about removing one electron and then the next electron and then the next electron. Well, we have just been discussing ionization energy. Remember, it started off with the definition as the first ionization energy. So the energy to remove the outermost electron, one electron. Here we're looking at, well, what happens if we remove the next electron and then the next electron and on and on. It's called successive ionization energy. There's an increase in ionization energy after each electron is removed from an atom. So this would be the first ionization energy. This would be the second ionization energy. So this ion is now having an electron removed from it. So it now has a positive 2 charge. And let's look at one more. So the positive 2 ion now has another electron removed from it, positive 3. So that's what we're talking about, successive ionization energy. Is it easier or harder to remove an electron from an atom that we've already removed electrons from? Well, the ionization energy increases as we remove more and more electrons. Okay, so question, well, why would that be? You could pause the video and think about it, but I will proceed. Let's look at the first atom here. Well, to remove its electron, it becomes smaller and has a positive charge. So that's this guy here. So ask yourself, well, it's going to be easier or harder to remove an electron from that ion? Well, it's both smaller and it has a positive charge. Because it's smaller, it's going to be harder to remove an electron. Remember, electrons are negatively charged. And it has a positive charge. So that negative charge the electron have makes it even harder to remove it. And then the next electron gets even smaller with an even greater charge. So, answer to the question, after each ionization, the atom's charge increases and its radius decreases, making it increasingly harder to remove. So every time you remove an electron, it becomes harder to remove the next one, becomes harder to remove the next one. This is called successive ionization energies. It always gets greater and greater and greater. Okay, now this is a table. You don't need to know this table, but you need to understand this table. Okay, so what we have here are the main group elements, groups 1, 2, and then 13 through 18, the S block and the P block. In blue here are the valence electrons that each one of those elements have, and then in the peach color is the core electrons. So sodium has one valence electron, and then all its other electrons are core electrons. Magnesium has 2, aluminum 3, etc., all the way to chlorine 7, and the noble gases 8. Okay, now, the main idea here is that the valence electrons are relatively easy to remove. Remember, they belong to the outermost energy level. But there will be a huge jump in ionization energy in order to remove a core electron. So if we were to look at sodium, it has that one valence electron. Well, it'll be removed relatively easily. But the next one, notice how the amount of energy, oh, and by the way, the energy is in kilojoules per mole. You don't need to do that. When we get to not our next unit, but the unit after that, energetics, we will become very familiar with the units for energy. Right now, you're just looking at a relative comparison. So we can see to remove the valence electron is 496 kilojoules per mole. To remove the next electron, it's almost 10 times as much. So it's a huge jump here. But then after that, it does go up, but not nearly as much, not nearly as dramatic. For magnesium, it has 2 valence electrons, and they are removed relatively easily, but then the next one goes up almost 5 times as much. And so you can see that trend happens at each step. A huge jump in ionization energy when we remove a core electron. So we can use that to identify what family an element is in simply by looking at where is there a large increase in ionization energy. Well, for aluminum, the first 3 electrons are removed relatively easily, but the 4th electron is a big jump in ionization energy. So that tells us we have 3 valence electrons. All right, so we'll do a practice on this in a minute. All right, let's do some practice. Which species has the lowest ionization energy? Well, for this, all we need to do is to ask which is the largest and has the least charge. Well, of course, that would be the first one. Largest, no charge. These others are smaller and they have charges on them. So it would be harder to remove electrons from them. All right, now let's look at successive ionization energies. Given the first 6 ionization energies for element X, determine its chemical family. So we can see the first electron, the amount of energy, the second, third, etc. Well, the big hint here is how many valence electrons must it have? So to answer that question, we just need to see, well, where is there a big jump in ionization energy? And we can see that happens at the 4th ionization energy. It steadily increases, but after the 3rd electron is removed, it goes up about 5-6 times as much. 5 times as much, which tells us that we have 3 valence electrons. So these electrons are removed. It takes more energy each time you remove an electron, but after the 3rd one's removed, the amount of energy to remove the next one jumps quite dramatically. Okay. So 3 valence electrons, well, that is the boron family. So X must belong to the boron family. Electron affinity. The term affinity means the attraction for. Electron affinity, the energy change that occurs when an electron is added to a gaseous atom. So it's like the opposite of ionization energy. Instead of removing an electron, you're adding an electron. The first electron affinity is exothermic, which means that energy is released. It's a negative value. You lose energy. So look at an example here. So to add this electron to this atom releases energy. It's exothermic. Now the delta E here, delta means change in, and the negative sign here, all of this is something that we'll talk about in topic 5, which is our third unit on energetics. So don't worry too much about the symbols and the negative sign and exactly what's going on there. Just remember that the first electron affinity is exothermic, releases energy. However, adding additional electrons is endothermic, requires energy, which is a positive value, as they are repelled by the negatively charged ion. So what we're looking at here is, okay, we've added an electron to this atom, but now it's negatively charged. Well, what if I wanted to add another electron to it? Well, in this case, we would have a negative charged particle being pushed into another negative charged particle, and they repel each other. So it's going to take work to do that. We didn't have to worry about that for the first one because the atom didn't have a charge on it. It was neutral. But now we're having to overcome the repulsive force of the negative ion that we're adding the electron to. And so that's going to take work. And so that's what we mean by endothermic. Energy is going to be positive. We have to put work into it, energy into it. Trend. None. To make comparisons, you must look up the electron affinity values found in the IB data booklet or elsewhere. This is a sample of the IB data booklet, and it has various numbers written in the boxes that correspond to the first ionization energy, electronegativity that we'll talk about next, and electron affinity, the first electron affinity and the second. So let's look at oxygen, for example. So you can see that the first electron affinity is a negative 141, and then the second, as we just talked about, is going to be a positive value, 753. Now, you don't get the second ionization energy for very many elements, as it's not very commonplace. So they're just listing here, as IB does, just the ones that are of most interest. Electronegativity is a measure of the attraction for a shared pair of electrons in a covalent bond. Okay, so let's look at the bond between hydrogen and fluorine. Of course, remember that dash represents a sharing, or represents 2 electrons, a sharing of 2 electrons. Because fluorine is more electronegative than hydrogen, it results in an unequal sharing of electrons. It forms a polar covalent bond. Now, this is something we'll talk about in our next unit on bonding. Right now, we're just interested in the electronegativity trend. So just trying to give you a sense of what electronegativity is. So don't be overly concerned about the covalent bond aspect here. But the covalent bond would be polar. And remember, we use delta symbols to represent positive and negative partial charges, which simply means that we have, for the shared electrons, more of them are over on one side than on the other side. And so the delta symbol there just represents that difference, the partiality of the shared electrons, partial charge. The 2 shared electrons are pulled closer to fluorine because fluorine just simply has a greater attraction for the shared electrons. And that's what we mean by electronegativity. So looking at these 2 atoms, fluorine is more electronegative. It's going to hold onto the electrons more tightly. Trend. Inversely proportional to atomic radii. The smaller the atom, the greater the attraction for shared electrons. They are closer to an atom's nucleus, and this should sound familiar. This is exactly the same as ionization energy. The smaller the atom, the greater its attraction for electrons, whether it's an electron that you're trying to remove from it, an ionization energy, or electrons that are being shared in a covalent bond. The smaller the atom, the greater the attraction for electrons. Just remember that. The smaller the atom, the greater its attraction for electrons. All right, now these are the three most electronegative elements: nitrogen, oxygen, and fluorine. Remember, atoms get smaller as you go across a period, and this is the first period, or the second period. So these are very small atoms, very electronegative. This will be important in our next unit on bonding, when we talk about what are called hydrogen bonds. Fluorine is the most electronegative element and is assigned the value of 4.0 using the Pauling scale, named in honor of Linus Pauling, who in 1932 first proposed the concept of electronegativity. He was just a really wonderful, charming guy. He died about 25 years ago, I think. Won the Nobel Prize twice, and he's an Oregonian. Here is a picture of him. The latter part of his life, he was a big proponent for vitamin C, thinking that vitamin C was a cure-all for many diseases, in particular for the common cold. He really felt that the vitamin C held the secret to curing the common cold. Unfortunately, it never quite went anywhere, but he was a really charming man nonetheless. Note, the electronegativity trend excludes the noble gases, as they have a completed valence shell and generally do not share electrons. So when you look up electronegativity values, more often than not, there's just nothing for noble gases, or they might not even include the noble gases in the chart you're looking at. You will see that sometimes there's electronegativity values because you can't force a noble gas to form a covalent bond. A few compounds occur naturally, but generally we just ignore the noble gases. Okay, now let's summarize the trends that we've looked at. As we move across a period and as we go up a family, atomic radius decreases, ionization energy and electronegativity increases. Remember that ionization energy and electronegativity are inversely proportional to atomic radius. So if the atomic radius gets larger, then they get smaller. If the atomic radius gets smaller, then they get larger. Okay, again, a little note here that the electronegativity increases, so as you go across, we would ignore the noble gases. Not the other two trends, though. Another way of looking at it is just a diagonal going from the lower left to the upper right, pointing to fluorine for the most electronegative. And that, boys and girls, is the end of today's notes.